Assalamu alaikum. A very good evening to everyone. I sincerely welcome you all into the International Conference on Power, Electronics, Communication, Computing and Intelligence Infrastructure 2026, which is hosted by Pabna University of Science and Technology, Pabna, Bangladesh, on the 17th of June 2026. Hi, Mahfuzur Rahman Kabbo, who is the presenter of our work on behalf of the team of Department of Electrical, Electronic and Communication Engineering from Military Institute of Science and Technology, MIST, Dhaka, Bangladesh. Our paper ID is 556 and our paper title is Design and Analysis of Hybrid Transmission Gate MTCMOS 4x1 Multiplexer for Low Power Nanoscale Circuits. This is the roadmap of our presentation. We will begin with the motivation and the problem statement, followed by our research objectives. Then we will walk through the design architecture, present simulation outputs, provide a comparative evaluation, and finally conclude with the future scope. Okay. So why this work is necessary? First, the rapid growth in battery-powered devices demands circuits with minimal energy footprints. Secondly, as we scale down to 90 nanometers and below, static leakage current becomes a critical issue. And third, in digital communication blocks, we need a careful balance between speed and power, often measured by the power delay product. These three factors drove us to seek a better multiplexer design. In the introduction session, the multiplexer or MUX is a fundamental building block in VLSI for data routing, signal processing, and memory addressing. Among its implementations, transmission gate logic is preferred because it uses fewer transistors and can pass full swing logic levels. However, as we will see, traditional transmission gate MUXs have a major drawback. The problem is very clear. Conventional transmission gate-based 4x1 multiplexers suffer from high static power dissipation. They lack any mechanism to disconnect the power rail during idle or standby modes. At the 90 nanometer node, leakage current drastically reduces overall energy efficiency. This is the gap we aim to fill. Our research had three specific objectives. First, to design and implement a hybrid MTCMOS-based 4x1 MUX architecture using Cadence Virtuoso at the 90 nm node. Second, to reduce the power consumption by at least 15% without incurring speed or latency penalties. And third, we validate our design by comparing its power delay product against conventional transmission gate and standard CMOS designs from established architectures. Okay, this slide presents the basic 2x1 transmission gate or TG-MUX architecture. So we move to the next slide with power gating technique, which is the core idea of this work. To tackle the high leakage, we use a well-known technique called power gating. The idea is to cut off current flow when the circuit blocks are temporarily inactive. As illustrated in figure 3, a high threshold voltage PMOS header switch acts as a power gate. This significantly reduces subthreshold leakage current during standby modes. So how does it work? Suppose we have a logic block which is powered by VDD source. And in place of this VDD, we create a virtual VDD node using the HVT PMOS, which is high threshold voltage PMOS header switch, which is driven by the sleep signal S. When the sleep signal S is 1, and we know when the gate is powered by high voltage or 1, the PMOS is off. So when the sleep signal is 1, the virtual VDD node is cut from the power. And at the standby operation, the leakage doesn't flow from here. And when the sleep signal is 0, this is short-circuited and the VDD becomes virtual VDD node and it operates correctly. So as we have seen that whenever the circuit is in idle state or off state, the leakage is saved here. So what is MTCMOS power getting into X1 TGL MUX? The idea is very simple. MTCMOS, which stands for multi-threshold CMOS configuration. Why it is called multi-threshold? Because these PMOS and NMOS used here are used using the standard threshold voltage available in Cadence GPDK90 library. And the power gating is done by a high threshold PMOS header switch. This multi-configuration of threshold voltage makes it called the MTCMOS power gating technique. How does it work? As we have seen already that we had VDD here at this terminal before at the basic 2x1 mux. And now what we do is we replace that VDD by the virtual VDD node shown in the previous slide at the power gating technique. So what we do is in place of VDD, we create a virtual VDD node using a high threshold PMOS header switch driven by the slip signal S. And using this, we can reduce the path of leakage during the idle state or off state operations. So this whole block is the proposed hybrid empty CMOS based 4x1 transmission gate mux, where the selection lines S0 here at the first stage is working as the first selection line, and the second stage, the S1 selection line, is working at the hybrid stage. So as a whole, this is our proposed architecture of 4x1 hybrid transmission gate based empty CMOS 4x1 multiplexer. We're moving into the simulation section and the result section. All the simulations were carried out using Cadence Virtuoso in 9TNM technology. Figure 5 shows the output or the functional verification of our hybrid empty CMOS based 4x1 mux. To evaluate our result, we compared our work with two existing literatures, which are shown here. The performance analysis, these curves show the performance comparison of the four architectures that was described in the last table. So here comes the performance analysis. Let me highlight the exact improvements. Compared to the conventional transmission gate 4x1 mux, our hybrid architecture achieves a 19.83% improvement in power consumption, a 14.23% improvement in propagation delay, and a very substantial 31.36% improvement in power delay product or PDP. These numbers validate our objective of at least 15% power reduction without any speed penalty. In conclusion, we have successfully implemented a hybrid empty CMOS transmission gate 4x1 mux architecture using 9TNM CMOS technology. The hybrid architecture improved power, delay, and PDP metrics significantly. This work contributes to the advancement of low-power VLSI circuits. For future work, the empty CMOS concept can be extended to larger multiplexers such as 8x1, 16x1, and even 32x1, and it can be tested under different process and thermal conditions. Thank you for your kind attention. I am Mahfuzur Rahman Kabbo. You can reach me at this email shown. I welcome your questions and feedback. Thank you once again.